We're going to go through the quest problems, but I am not going to do them for you. All right, we're going to use all of our collective brain power to try to figure these out. I will be here to point you in the right direction, because What?
So you're going to do them?
No. Because I know with how many smart kids we have in here, we can figure them out. But first off, yes, all the Asians.
It's not as many as our class.
All right, first off.
These are all the Asians in our class, yeah?
All right, let's go over the equations first, just so we're all on the same page.
Go to 3.
Okay. And you'll see that I have names for some of them. You'll catch on if you don't know them. Oh, but these are just the basic kinematics equations. I'm writing them in the x direction, but we're going to see later that these also work for the y direction. Yep.
How do you know that?
Because he's brilliant. Okay, I'm going to write 3 more equations up here. They're technically not kinematic equations, but you need to know them. The first one is the average velocity equation. So this is Vave. I know my handwriting is horrible. Vave is equal to Vf plus Vi over 2. That's just the average velocity. That's how you take an average of something. Add the 2 values, divide by 2. Number 5 and number 6 are what I call definition equations, meaning that if you define, for example, velocity, you can define it as the rate of change of distance over the rate of change of time. Okay, I assume that you knew this equation for the people in my class.
Wait, is VI
which was, yeah, same thing. Which was a mistake on my part. I thought you knew this, right?
We have to learn.
I know, but I thought you knew it just because you're smart.
What's the jump?
Oh!
Okay, x is d. X and d are interchangeable. It's displacement. So when I'm using, I'm trying to show you all different ways it can be written, because you'll see it a bunch of different ways. This is for displacement in the x direction. You can also see delta y equals vit plus
What is VI?
initial velocity. It's like v naught t.
Whoa.
So it's delta x, delta d.
Yes, it's the same thing. These are the exact same equations I showed you. I'm just writing them differently so you can see. Like I said, you try to teach yourself this stuff. Your professor in college might use it differently. It just depends on how you're writing. They're all the same equations. So, number 5, we know velocity is the rate of change of distance over time. Okay, it could be delta x over t too. The other one is our acceleration definition equation, which is change in velocity over change in time. Rate of change of velocity with respect to time. Okay, number 5 and number 6, if you were in my class, I did not give you those because I just thought you knew them, which was my bad. But they're really easy, but you do need them for the quest homework. All right, I know some of you have already started this and gotten some of these right. So we're just going to start from the beginning because it's not going to hurt to go over them again. All right, 1. Let's start with number 1. I know a couple of you already got this one correct. This one's basic. What's the basic solving process with kinematic equations? Well, before you do any of that,
You have to, you write out the given.
okay, yeah.
I can write an equation if you don't know.
Right, if you don't know.
So-
Get out
And
of
it's
here.
not what you have, it's what you
Get outta
don't
here.
have, Mr.
What you don't
Flores.
have.
It can be, yeah, you can do it that way. So for number 1, if you're writing out, now keep in mind you're all going to have different numbers because that's how Quest works.
Why?
Because the people like you, that's why.
Can't cheat anymore.
Yeah. Okay, so in number 1, well, I'll step you through this one a little bit more than I'm going to step you through the other ones. So number 1, basically when you read the equation or the problem, you should write down what you're being given. You get an initial velocity of, in mine is 10.9 centimeters per second. Yours might be between 8 and 12, I don't know, but it should be in centimeters per second. You're going to get an initial x measurement, initial displacement of 3.16 centimeters from the origin. You're going to get a final x value. Negative 7.57 was mine. Yours should be negative something. I believe that's how it's set up. And then you're going to get a delta t. 963 seconds. But basically the problem says there's an object moving at this speed initially, its position is this initially, 0.963 seconds later it's at this position. What is the acceleration of this object? Okay, so what you would basically do is you'd look at those 6 equations and try to figure out which one has this, and this in it, and this one. Oh, I forgot the order, yeah. It is going to be number 3. Okay, number 3, I wrote it as delta x. Keep in mind, these two values right here will give me delta x. Final minus initial will give me change in. So you'll see it, that equation can be written another way. Even another way to confuse you, but that's just how it works. All right, so in other words, we have delta x, initial velocity, change in t, and acceleration. You look at equation number 3, it has all those things in it. So you write out equation 3. I think the easiest way to solve these problems is to rearrange your equation first and then plug in your numbers. So what am I going to rearrange for? A, acceleration, right? Okay, when you do that, did I do this on my paper? Yeah, I did. You should get this. A is equal to 2 delta x minus bit over t squared. I'll let you look at that algebra for a second. But like I mentioned before, the algebra should not be the most difficult part of this class. It's the problem solving that's going to get you tripped up.
I keep writing delta.
Okay,
D.
one suggestion I have is if there's a fraction in your equation, so like equation number 3, and if you're using the average velocity equation, the first thing you're going to want to do is multiply everything by 2.
What?
Well, because you cancel out for 1.
Right, so you get rid of that fraction and it makes things a lot easier. So get in that habit. If you're using this equation, your delta D equation, change in x equation, then go ahead and just first thing multiply by 2. And then when you rearrange, it should be pretty easy to see how I got here. And then at this point, all you do is you just plug in what you're given. So it'd be 2 times change in x is going to be final minus initial. That's always change in, final minus initial. 757 minus 3.16. Okay. I'll double up on those parentheses. Right, change in x. So I find out what that is first. Minus my initial velocity is 10.9 in this case. Times 0.963, sorry. 0.963. Okay, that's the top of my equation. Close that out. The bottom of my equation is just t squared. And then you just put that in your calculator. I was doing something weird in my calculator. I couldn't get this answer from out of it. Hopefully you guys know. Otherwise, I know I didn't mess up right here. I'll just start with this. As far as them, so for the free response, that would be the only time they would expect to see that, and it depends on how they set the rubric set up. But from what I know, from what I've seen, I've never seen a point value associated with the equation being rearranged. I've seen a point value associated with the equation being written down, but I don't think I've ever seen it for it being rearranged. Have you?
I have not. But they will not, like, if you do it this way, you're sure to get points. Whereas if you plug it all in first and then try and rearrange, they might not. Then it's up to the evaluator whether they get points or not.
From what I understand, the old school method is plugging in numbers first and then rearranging, because that's how I was taught in high school. And then in college, I was told to do it the opposite way.
Well, you're grumpy.
Yeah, I know. I'm a dinosaur,
Are there
right?
any more iPads?
No. You don't need one. Okay, so that's 1. Let's go ahead and look at 2. So from here on out, apart from a couple questions, the difficulty is going to be in realizing some assumptions about the problems. That's really what trips people up in physics is there's assumptions that can be made based on how the problem is set up. And that's really what's going to be the issue with number 2. So hopefully you have either this printed you have the Quest stuff printed out, or you have a laptop or something to look at it on.
Real quick.
So
This one need an iPad.
All right.
Guess who's out there?
Did anybody notice any issues on the last one? On the last problem, problem 1? No? No issues? Okay. Because
Because it's negative.
Gotta go back.
It's a negative number.
what about the negative number?
There's no
It's
such
not
thing as
supposed to be
negative
there.
distance.
Huh?
Yeah, there's
negative time, yeah.
negative time. Negative.
I forgot to mention that. That was a good catch.
Negative time?
No,
Oh,
no, that's on a different one. Sorry.
Yeah, no. So one of the problems that I had questions about is the fact that I have a positive velocity, but I end up at a negative distance.
You go back in time.
Yes. Exactly.
Is that possible?
That's how you solve.
Yeah, it obviously
Why not?
is. It's telling me
Oh, maybe if you move the origin, then technically
you can't move the origin because
Yeah,
you're
the
not.
origin
you did that in the
said-
lab.
We had a big
No,
argument
you
about
didn't move the origin.
Okay.
Yeah, we moved the
You
origin.
moved the starting point. You didn't move the origin.
The origin
Sorry.
is always
Yeah.
Always
zero,
gonna be 0, 0.
So like this was a big issue and we had a big argument about it, but if okay. So if positive velocity is this way, right? And the x is positive that way, you can still have positive velocity and end up in the negative. Make sense? So you're moving this way.
Yeah.
Does that make sense? So you're moving this way but you're slowing down, so you have a negative acceleration and you end up at the negative origin.
Like the little car.
Make sense?
Yeah, it's like when
Yeah?
Yeah,
the
it's
car,
like with the car.
Okay.
car went up the hill.
Yeah.
So we had like 2-hour discussion about that. Alright, so my bad. Go ahead.
No, that's a good point.
Okay.
Number
Sometimes some
2.
people tripped up with that.
So number 2, I know. Let's see. Jay got this right. Number
I
2,
got it
right?
right.
The particle one.
So we got it right.
You get okay. So some of my students have gotten this right. I know that. The Asians got it right. Okay.
It's because they all cheated off each other.
Number 2.
I don't have
All right.
to games up.
Let's get through number 2. Shh. All right, 2. Yeah. Go back in the closet, Florence. He comes out of the closet every once in a while. Yeah, that's the joke. All right.
I know.
2.
He was telling his other class that I just came out like,
Yeah, they
like
kept,
no, well in the closet.
they when you went back in, they kept asking like, when is Flores gonna come back out of the closet? One of my students didn't realize that went to your room. They thought that you were just in there the whole time.
Oh my god.
All right, sorry.
Okay,
Let's go. Yeah. Number 2. All right. So if you're reading through two particles moving along parallel paths in the same direction, pass the same point at the same time. Particle A has an initial velocity of 7.5 meters per second. All right, and you get velocities and accelerations basically. All right. So you've got 2 particles, A and B. Right. They are moving, and at some point, one is going to pass the other. And they're going to have the same what? What value? Displacement or x, whatever you want to call it. The x value is going to be the same. Right, that's what it's saying. So what assumption can we make then?
One fast.
Okay, what? Okay, so we can say, let's not say that they start at the same place, but let's say that where they start doesn't matter. Let's say that where they start doesn't matter. What can we say about, in this situation, since they've reached the same point, what can we say about the final position of A and the final position of B? They have to be the same. Okay, since they're the same, we don't really care about them in this problem. Okay. We are being given a velocity for A and an acceleration for A. We're also being given a velocity for B and an acceleration for B. What are we looking for? Isn't it the time first, right? It's the time first, right? Yeah. Okay, so we're trying to figure out at how many seconds do they have the same position. All right, so we've got T, VA, or velocity in A. These things are important, but we're assuming that they don't matter. I know that sounds weird.
They don't matter because they're equal.
Yes, they don't matter because they're equal, but we are being given these things. So we can include them in like our search for the equation. Sorry? Right. We're going to use, if you were writing down what I wrote up first here, we're going to use the third equation because it contains displacement, velocity, acceleration, and time. Yeah.
If they don't matter, why are we using them?
Yeah, that's what I was trying to explain. We are being given this information.
So we
Like
have
I would
to-
write this as a given, but what I'm saying is ultimately it doesn't matter because they're the same. But I'm gonna look for an equation that has that in them because it's part of the problem.
So could I just scratch these
You'll see.
variables out of my
Yeah,
equation?
exactly. So you'll see what I mean when I write this down. Okay, so we're gonna use this equation. Delta x equals bit plus 1/2 at squared.
We're solving for t.
Oh, there's one more assumption we can make.
No, no, she's leaving.
Okay. What's up? Were you able to do?
Yeah, and then you wrote it down for me, so now I really can look at it.
Cool. All right. Sweet.
So triangle x is what?
All right. So basically, if you see this equation, you're gonna get what I mean. All right. Because they're reaching the same point, their change in x has to be the same for each particle. All right. Their change in x has to be the same. So really, what we're gonna do, if change in x equals change in x for both particles, we can set the second part of this equation equal to the second part of the equation for the other particle. It would look like this. And we get kind of complicated with our labels, but we would have the initial velocity of A plus 1/2 the acceleration of A times the time squared equals initial velocity of particle B plus acceleration of B. Okay, that's what we get. Okay. The issue with this is the algebra, really, with this problem. Messing with my mouse.
Yeah.
Yeah, make it.
The T's. The T's.
What?
The T's.
Oh.
The IT.
Oh. Good call.
Yeah.
Why would we put that there?
That's what the equation says. I forgot it. It's VIT plus 1/2 AT squared.
But what is VIT?
Initial.
Initial velocity times time.
V naught.
And then I'm just labeling particle A, particle B.
Okay, you guys were saying V naught squared a lot in the first class, and
I know. Like I said, I'm going to show it to you both ways because you're going to see it both ways.
It's not
Also,
squared.
VIT is
Seriously, physics
initial
gives
velocity
four
times
names for
time.
everything.
Times time. V naught is
Minimum.
the initial velocity too. It's the same thing there.
So,
They're the same equation. It's just a different way to write it. All right. So like I said before, if we're using this equation, do this. Multiply everything by 2 to get rid of your fractions. So you're going to have 2 VI AT plus 1/2.
no.
Sorry.
It's done.
Good call. I'm trying to do this too quickly. Plus AT squared and 2 VI AT plus AT squared. Okay, we're trying to solve for t. The best way to do this algebraically is we're going to go ahead and move everything to one side of the equal sign because every term has a t in it. So we can't isolate the t by moving half of it to one side or something like that. We have to put everything on the same side.
Yeah.
You can subtract t to the left side, then you subtract t squared to that, so then you divide by t. Technically, you're dividing by t. Why would you?
You can't divide by t. You're going to need to factor out a t. Because you've got t and t squared. You'll see what I mean. You see what I mean? Just let me work through this. It may end up being that we do the same thing, but this is how I would solve it. All right, so we're gonna move everything to one side. 2 VIAT plus AAT squared minus 2 VIET minus AET squared equals 0. So all I did is I took this right here, subtracted it to this side of the equal sign. Yeah, it's a lot of writing. Okay, now I see that every term, they're on one side, every term has a t in it. So I'm going to factor out a t, right? So it looks like this. Let me go to the next. T, 2 VI A plus, what is it, AT, right? Minus 2VIB minus AB equals 0. You can actually go a couple different ways from this point. You can see that there are two things in common with the velocities and the accelerations. So what I would do is, let's see if this makes sense to you if I do it in one step. So the t is still factored out. What I'm going to do is I'm going to take the 2 here and factor it out of the velocities. So I'd have 2 times VIA minus VIB.
No, it's all he did was he should have wrote 2 T's, but he wrote T then 2.
Well, I'm just trying to show you, yeah, I could write 2, well, no, because I just want this 2 to be distributed here. I don't want it to be distributed to everything. And this is going to be, yeah, this is plus T acceleration sub A minus acceleration sub B equals 0. No.
No, we got
You have to do a little bit more, but now you can see that there's clearly 2 parts, right? Here's where some algebra comes into play.
This was an algebra.
Well, some more, sorry. Okay, I have a t out here, and then I have a term here. Okay, this equals 0. What's one solution for t?
0.
0, right? So basically what we can do is get rid of this t that's floating out here. And we're going to say one solution 0, let's get rid of that one. And now we're going to look inside here. Right, so this is my new formula.
Oh, it's like at the end of the year when they're like, tell us how many T's you know. When we started doing hyperbolas, and it was like T to the
Yeah,
fourth.
if you've done this when you're solving for parabolas, probably.
Thank you.
Because you're going to have like a y-intersect of 0 or something like that. One of them will be 0 and the other is the actual value you're trying to solve for. It's the same thing here.
Whatever.
0
Just trust me.
minus 2.
Wait, so if we assume that one of the t is 0, can't we just make that equal 0?
No.
Because there's another
Because
T.
that doesn't get us
No, I
anywhere.
mean, I'm talking about the left part. Then.
Yeah, the whole thing would be equal to 0 if t is equal to 0. So we're going to ignore that solution. What do you say?
I'm gonna become a poet. That's what I'm
He saw my comment. Just trust me, right? This is what you do. I'm probably not the best person to explain the algebra behind this, actually, because no, yeah. I know it works for physics. I don't know what you're actually supposed to do. So this works for physics. Okay, let's just leave it at that. So here, now what I'm going to do is, you'll see in this part, I only have a t over here. So now I can solve for t pretty easily. So you're going to get t is equal to, hopefully I can do this in 2 steps, 2 VIB minus VIA. You'll see that these switch places. Why? Why did these switch places? I moved it to this side. Okay, so these switch, I switched the order that I subtract these in because of that. Divided by this term.
What'd you get?
And then finally, you can plug in and get an answer for this one.
Alright, wait, can you like go back one slide? Like, I want to see like if my way.
Okay, yeah. Let me have this one up just for a second so people can write it down. So really what makes this problem hard is the algebra. And
Yeah.
some of you are going to get the algebra and it's never going to be a problem. Some of you, it's going to be something you struggle with this whole class. I'm just going to be honest. That's what it has. Yeah. That's what happens. Yeah.
What?
Something.
Who's gonna win this weekend, Mansell or Dan?
Mom.
Nick Mansell.
I'm going to score with your mom. That's
That's
Alright.
a little nasty.
what was your
You can do
thing,
better.
Kevin?
Teach me.
Go. Alright, okay.
Go, teach me.
So you're given this equation,
Yeah.
right? So can't you just plug in what you're given here? And so this is t, so so whichever t is the highest or the lowest, you subtract that, and move it to the left, and you get t, just t, not just any. If this t was like the lower t, then you just subtract to this side, and you get blah 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 t equals blah 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 t squared, and you just divide off the t. If you count out algebra, that's possible.
So you went ahead and plugged in your numbers at this point?
Yeah.
Is that what you're saying?
But I didn't add them like yeah.
Honestly, if it was me working out this problem, I wouldn't have gotten past this step before rearranging. For this, and I don't want to say do this. Yeah, but for this problem, to me, it makes a lot more sense that I put the numbers in here, because it kind of saves you on some of the algebra. But I'm just saying it's better practice to rearrange first.
If we have a test, will you come up with it?
No, I wouldn't. I wouldn't care. If you showed your work and you got the right answer, then I'm recording this. Hopefully it's gonna be on my website.
Where's the recording?
It's capturing right now.
Oh my gosh, I just got back from practice.
Does it have audio?
What's up?
Audio.
Well, it's better if you're here, to be honest. Really? That's the first thing you do when you realize that there's a microphone. You make a fart noise.
Oh, so they can hear our conversation?
Well, I'm not streaming this. All right, let's look.
So guys, on the internet, you see the butterfly.
Future Alice, you are beautiful.
I'll be so upset.
Let's see, for 3.
Positive note of the day.
3 is actually really easy.
Wait, how is it easy?
Yeah, so what you're going to do for part 3 is you're going to take the time you solve for and use it now as another given, basically.
Oh,
So,
and you're finding delta x?
yeah.
Oh.
Okay, so you have t, I'm just going to make up something, t equals 5 seconds. That's what we solved for, let's say, on the last one. That's my new given. I still don't know what this is. I'm trying to find what change in d is. In other words, where do they intersect? I know their accelerations, and I know their initial velocities. Should be obvious which equation this is.
3.
Which velocity? Are you second equal to again?
Oh, it's 1?
No, okay, that's a good question.
Because
It's
you
3.
need to find delta D, so you would.
Right. Okay, so here's a really good question, because that was my first thought too, was I need to set them equal to each other again. But keep in mind what we already solved for. We know at t equals 5 seconds, for example, they're at the same position. So it doesn't matter which set of givens I use, as long as I'm consistent. So if I use the acceleration for A and the initial velocity for A, I should get a distance. If I use the initial velocity of B and the acceleration of B, I should get the same distance. Because we already solved for that's t where they intersect.
But if they weren't, they weren't.
Yeah, but if they weren't the same, we couldn't have solved for that in that time at the last problem, because they would have never intersected those two parabolas.
Which velocity did you use?
It doesn't matter. You could use either. That was my point. We know they intersect at this time, so they should, if we did the math right, they should have the same delta V values, as long as I'm consistent. I do A and A or B and B.
Are we
Oh,
talking
'cause they
about
cost
this
the
problem
same
or
time.
the last?
This
part
is
of the
part
problem?
2. This is part 2 of the same problem.
And we're talking about consistency on part 2 or part 1?
So basically what happens is you get a time from this, and that's the answer to part 1. Now that's a given in part 3. So now I know the time I'm trying to solve for. I just need to find out what distance that particle has at t equals 5 seconds, for example, if I solve for 5 on the last part.
So it doesn't matter
Are
if I
you
put
like
A or B,
saving
right?
your screen or
Yeah,
something like voice
it should work, hopefully.
Wait, is it, so you can
If it
put
doesn't work, it's because my laptop is holding it. Yeah. What?
So you can put A or B.
You can use A or B, you should get the same answer. I didn't test that, but you should.
I just did it.
It did? Yeah, okay.
Go Jude!
See, I'm right. An Asian says I'm right, so I'm definitely right. 4. I don't remember which one 4 is.
You should do shortened clips. So
Oh.
it'll be easier to upload.
Yeah, that I should have done that next time. Okay, 4. This is probably the most challenging one. 4? Yeah. 4, yeah. You're going to see problems like this on the AP exam. Physics is notorious for having very vague descriptions of situations, and you really have to get in the the question writer's mind as to what's being given to you.
Ravine, man. This was
Okay.
actually fun.
So basically, here's the situation you have in problem 4. This
It's a
is
terrible stick figure.
yeah, I know. Actually, that looks kind of rude.
It's
let me
like-
fix
I get it.
I didn't mean to do that. That was
Yeah.
an accident.
totally just
It's a
happened.
telescope.
It's a telescope, yeah.
Oh
Okay.
my
Oh, it's a
god,
peak.
this is
It's
like.
okay.
Is that what
I
it's
drew
called?
swastikas in all of my.
Guys,
all
we're
of my
AP
classes.
Physics B students. We can be mature about this.
No, you can't.
What was it?
All right. Well, he's a black stick figure man. You can guess.
Oh, it's black. Why can't it be?
I couldn't. I need to zoom in.
Oh, I get it. That was funny. Ha 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 ha! I quit this guy.
Wait, did he say he was Asian or black?
It's Asian.
All right.
Obviously he's black.
So basically in this problem, this is what you have going
It's
on.
misleading.
You're on this cliff. There's a ravine, meaning like a gap, right? That heads over to a cave.
Wow.
It looks something like this.
He gotta jump.
What kind of?
No, it's
How do
like
you get there?
okay. So
Water.
Oh.
Cuts it.
yeah, let's say there's like water down here. Okay, what they're saying is the length here to here, right? This is the length of the ravine. I'm gonna label it down here so it's kind of out of the way. In my problem, it was 10.8 meters.
Mine was 13
Yeah, something like that. Yeah. Okay, so we have some x distance, in other words. And you can see this clearly from the picture. This is why drawing pictures is so important in physics, so you can label x and y. This is an x distance. What they're also going to tell you is that the cliff overhangs from where your feet are on this cliff over here. It overhangs some distance. Mine was 9.2 meters here. Right, so from here to here, that's 9.2 meters. It overhangs. And then the very last distance they give you is, it says the cave has a vertical back wall, which I didn't do a good job drawing it vertical. Vertical back wall, that is, in mine, it was, no, hold on, it was 4.2 meters deep, yeah.
So does everyone have a different?
Yes.
Yeah, everyone has different numbers.
Yep.
So,
oh, that.
there's three distances you're being given. An x value between the cliff and the cave, and then an x value between the mouth of the cave and the back of the cave. And then you're given a y value, basically how much lower is the overhang from where you are up here. That's what you're being given in this problem. The very last piece of information, which is something you're going to have drilled and etched into your brains, oh, that was weird, is this. The acceleration due to gravity on Earth is 9.8 meters per second squared. That is something that sometimes you'll have to assume.
But is it
At sea level.
We're going to say it's positive. I know it's weird, but I'm going to say it's positive.
On the AP test, you can use 10 on the map.
Yeah, if you want to use 10, well, we're going to use 9.8.
What- yeah,
That's
we'll
being
use
given.
9.8.
If it says A is 9.8, you use 9.8, not 10. Okay. The first thing it asks for is at what horizontal velocity, so I'm going to do Vxi, right? Velocity in the x direction initial. At what horizontal velocity do I have to kick a rock in order so that it just falls past the overhang? Right? It's not going to hit the overhang, it's going to go just under it. I know this sounds really weird.
Stupid. Nobody thinks about this. Like,
No one,
yeah,
no one goes there very close. Like,
Hey.
all right, rock.
Hey, I
know.
calculate every time I
Right,
kick a rock.
yeah. Pre-rock kicking
Free rock.
calculation.
Oh yeah. All the time.
Why don't you just throw a freaking rock back, like right below you?
Would
So
you-
you have to calculate it.
Alright. You're not in med school yet, Kevin. You have to learn physics first.
Yep.
Okay, so we are being asked for the horizontal velocity. The initial horizontal velocity that I have to kick this rock at so that it flies across and just goes under the overhang. Okay, this is technically, you could probably label this as a two-dimensional motion problem, which we are supposed to be doing
Yeah.
no, next time in class. But we'll see. Here's what's going on. We need to solve for something before we can solve for that velocity. We don't have enough information being given here so that we can solve for this. So let's look at this distance here first off. Is this in the x or y direction? Okay, this is in the x direction, so I know this is going to play into this somehow.
Oh, triangle.
It's going to play into that somehow. No, let's not get to the triangle business. Right? This is not a triangle, it's an arc.
No, but would that be 90 degrees and they find the particle?
Yeah.
The
Well,
circle. Of a circle. Damn.
it's not necessarily a circle.
You guys are thinking way
Is that
too
hexagon?
complicated.
Yeah,
man.
I know, I just, whoa.
You guys are way
Okay,
overcomplicated.
what about this? X or Y? This is also X, so that may play into this. It's actually going to play into part 2, so we're not gonna look at this yet. This is what?
Practice, you need to move your cars before
This
they
is
are
a Y
sent.
measurement.
Thank you.
Okay, this acceleration right here, is it an acceleration in the X direction or in the Y direction? Y. This is in the Y direction as well. So
why is it Y?
it's the acceleration due to gravity.
Oh, because
and it's
Jump on
always-
that real quick and tell me why.
yeah, it's going to point towards the center of the Earth. It's always going to be Y. So basically, in physics, we have to separate the X and Y values because they don't really interplay with each other, at least in the type of physics that we do. So, for example, I would not want to associate this number with this because they're going in different directions. It's like when we did vectors, we had the X and Y components. Right? And we only combine them at the very end. That's kind of what we're going to do here. Keep them separated until the very end. So in which direction, X or Y, do you think we have more valuable information?
obviously
Y.
Y, right? Because we have an acceleration.
Yeah.
Okay, so we could say in the Y direction we know a couple of things. And we're going to have to assume some of these things. First off, we know the acceleration is 9.8 meters per second squared. Okay. What else do we know from the picture?
Sounds about 9.2.
We know our change in Y is going to be 9.2 meters. Okay, there's a couple of other things that we can assume. Well, one we can set by saying this is the origin.
So it's negative.
No. Well, yeah. Sorry? Well, that's not what I was drawing here, but okay. No, that's really the last thing we need. So V initial or V naught is what?
0.
Okay. I know this is counterintuitive to some students, but when I kick a rock perfectly horizontal, the microsecond that it leaves the edge in the Y direction, it has no velocity. It's not moving up or down. Now, immediately as gravity starts pulling on it with this acceleration, yeah, it'll have a Y velocity, but at the very microsecond that it leaves the cliff, there's no Y velocity. So we can say initial velocity Y is equal to 0. Okay, what could we solve for with this information?
You know what you can solve for.
Look at your equations. that you
VF?
have. Sorry?
Yeah.
Okay, we could solve for VF. Yeah.
We don't want to go.
Oh,
Okay,
wait.
Would that help us find this, though, do you think? Because it's not...
What's X again?
Okay, here's the thing. VF is still going to be in the Y direction. There's one variable out of all the ones we've looked at so far that we could take in the Y direction and apply it to the X direction. What is it? Time. Okay, time is going to be the same in both X and Y.
We gotta use the same formula we've been using.
We're going to use that one a lot.
Would love that.
Okay, so this is a
Marry that
really big
equation.
realization for first-year physics students that haven't done projectile motion before, is that the amount of time the object spends moving in the Y direction is the same amount of time the object spends moving in the X direction. They're the same. So if I want to bridge between X and Y, time is always it. So a lot of times with your projectile motion problems, your first step is going to be to solve for time. Right? And this is one of those problems. So what I do is change in Y is equal to VIT plus 1/2 AT squared. We can cancel out one of these terms.
Time.
No, it's not time.
Acceleration.
No, we have acceleration.
Velocity.
I'm guessing
Just
something.
guessing.
Velocity
man.
initial 0, so I can rewrite it a little bit simpler like this. Okay. Solving for t, I'm going to get the square root of 2y over a, 2 delta y over a, however you want to write it. So I could plug in and solve for t that way. Fine. 2 delta y over a is what you should get when you rearrange for t here. I would multiply through by 2, and then I'm going to divide by a, and then take the square root of that.
So we're trying to find t right
So yeah, right now the problem didn't ask us to solve for t, but in order to bridge y and x, we have to solve for t. That's the only way we can go between the two
Sure.
axes or whatever you call it.
What are you trying to find?
Okay.
Wait, so that t right there is the final equation.
The t is what?
That's the equation from the bottom left.
All I did here is I took this, I canceled out VIT because VI is 0, and then I rearranged this equation for t.
Okay.
Right? So I could plug in here, plug in my numbers, get a time. Let's see, did I do that on my paper? Yeah. So you're going to get t is equal to, here for this problem, 1.370 seconds. Okay. So that's the first step. And like I said, when we start covering projectile motion, next class period hopefully, that is going to be the first thing you do in almost every projectile motion problem is solve for time. Did you have something to add?
Yeah, so like, real quick, you guys are asking why I solve for t, right?
Yeah.
Okay, so you look here. What are we looking for? What's our final answer going to be that we're looking for? Velocity. Which velocity?
Of x.
Well, in the x direction here, right? Does that velocity ever change in this direction? No, it changes in the y direction, but remember, velocity in the x never changes, okay? Unless we're applying a force, right? But we're not doing that. So since velocity in the x is never changing, it's an average velocity. What's the equation for average velocity?
The one that
D
you
over
gave
t,
us.
right? Do we have d? We do, right?
Yeah.
We have delta v right here. So what do we need? Make sense?
So like what I've already.
Exactly. So that's why we're solving for delta t. So we can find average velocity, plug it in, and we're done. Make sense?
So we're gonna use multiple.
Oh, yeah.
To find t, you have to use a certain formula.
Exactly, because when you look at it, you're looking for v average,
Are all the
right?
problems like this hard?
Which is delta v over delta t. We don't have delta t. So you have to find the formula to find delta t, which is this formula here, always. See what I mean? Yeah?
It's just so hard for I remember this
Okay.
before and it's just like
Right, I
Like
feel
a
like
slap
it's
on the
easy.
That's why you're here.
Just a small slap in the face.
No,
I feel like
you
I
slap
feel
in
to
the
create
face.
t.
like if I didn't come here like number 4, I probably would have typed in I don't know the answer. And I would've just
I
said,
That would've been wonderful.
Last time I kept doing random answers until it finally told me I failed.
Nah.
Yeah.
Okay, so we found t, right? And now we can just plug it in here and get an
The
answer.
second part's really easy.
Hey, I gotta save t.
You did?
Yeah.
You're lucky. So all I would do here is, really the only thing that would trip you up on this problem is if you get your x and y's confused. So we already used this distance up here. I don't want to use it again. Which x distance am I going to use to find out the horizontal velocity? Sorry? Did somebody answer me? Try to find the horizontal velocity that's going to get it from here to here.
Why 10.8, not the whole thing?
well, cause like
It looks like the bottom.
Yeah, we're looking for just right here,
Yeah.
right? Okay.
No, I have a question.
Yeah,
How do you get to point in the beginning?
that was given.
Given.
We have to subtract, add,
No,
move,
it was,
and-
no, it was right in the problem. So you just do this. And what you would get is the velocity that you need to kick the rock at. So it would miss the overhang.
so that's the answer.
Yeah.
What is that?
Now for the second part of this problem, number 5,
Oh my god, it's
It's number 5.
I'm not going to work this one out for you.
so god.
Okay, number 5, what it asked is, let's go back to our initial picture.
Oh.
It's easy.
Number 5 is going to ask, so this thing's going to curve and it's going to hit the back wall somewhere.
Yeah.
What it's asking is, how far from the top of the cliff does it, no wait, how far from here does it hit the back wall? That's what it asks. How far from here does it hit the back wall? Okay. So there's a couple of ways of doing this. Let's see, how did I do it? Yeah, that's a good question.
You guys tell me, what are you going to need?
some extra information.
Okay.
Yeah.
Time.
So
Time's important, right? Is it going to have more time or less time?
Do you know what one?
Why?
Because it takes farther.
Yeah, further away, right? Cool.
So yeah, what you're gonna do again is, I'll get you started on this.
Yeah, we had the same number. We had a different bottom.
Okay. This is, oh, hold on. I lost myself in my work.
I believe you're looking for the
Oh,
function.
wait.
Yeah.
You do? Okay. Do you guys have a velocity? What do you have? What do you know?
That one doesn't give us any more information.
No, it doesn't.
Well, exactly. But you already solved for some things before, right?
We have
velocity. Okay. So do you know if you have velocity, right? And now you know the distance that's going to go. Okay. What can you solve for? Yeah, time. Does that make sense?
So looking back at this picture, now we know how fast it's moving this way. So we know it's going to move a total distance of these two things. So what we would do is we could find the time by using our velocity definition equation. So we'd actually use this one first. We'd say the velocity in the x direction is equal to delta d over delta t. Delta d being those two x values that we had, because now we're looking at when it hits the very back of the cave. So we need to add those two, and then solve for delta t. Right? And then you're going to go up here and plug into this equation to solve delta y. I'm going to let you guys figure out what the correct answer is. I'm going to give you a hint. The number you get here, if you put it into Quest, it's going to be wrong. You have to think about what you're solving for in terms of this picture. Okay, remember that it's asking how far down the cave it falls, not how far from the top of the cliff does it fall. So it's just one more simple step. I'm gonna let you guys figure that one out. Let's see. Which other ones do I want to touch on?
Your acceleration.
So number 5, you're looking.
6 is easy.
Acceleration is always the same.
7 is easy.
Constant, 9.8.
You should be able to figure out those by this point.
4, and there was one number that was delta u.
Why is the one that you notice the K on the opposite wall?
Yeah, so
The ceiling is like your feet.
Number 5 is, it's like the opposite of number 4. So number 4, we have more information in the y direction, so we solve for time there, and then solve for
I
velocity.
found the delta y, but what on the picture, what do you like? So you're looking through this.
Yeah. No. You're looking for how far from in the cave it falls.
Right. So for number 5, are you looking for delta t?
No. You'll find t first.
I mean delta d, delta. This,
Right. Change them y though.
Okay, so
2 delta is radical, 2 delta y over.
To find the time?
Yeah, and that's a change in first number itself.
That's t, yeah. And then you're going to use that in your average velocity definition equation. Delta v over delta t. It shouldn't be that small. Like my answer was 8.50 meters. You should get a delta y that's about twice as big as the overhanging thing.
Is the time like 1 point something?
Yeah. Did you square time in the? What do you? There's one I got a negative time on, but I don't think it was 2. No, wait, no, I did. Yeah, so if you got a negative time on 2, when you factored out and moved one of the terms to the other side, you forgot to switch the order. So, like if it was VA minus VB, if it moves to the other side of the equation, it's now VB minus VA. And that, I think that gets rid of the negative. But you should have gotten the same value. This positive or negative instead of positive. We need to move on. Can you figure it out? Yeah, if you multiply this through, I can do it.
No,
All right.
wait.
No. Bad Kevin.
The 5 makes no sense at all.
No. So okay. So here's the difference between 4 and 5. All right. If I'm going to summarize it, 4, you have more information in the y direction. So you're going to solve for t with the y information that you have, and then you go over to the x part and solve for what you're being asked for. In 5, it's the opposite. Now I have more information in the x direction, so I'm going to solve for t using the x values that I have, and then go over to the y and find out delta y. Yeah. You're actually using, here's the other thing, is you're using the exact same 2 equations that we used in part 4. It's just the order that's different. And for almost all of projectile motion, those are the 2 equations that you use.
Okay, so it says, you notice the tape on the opposite wall to the ceiling is 7.1. That is delta y.
Let me make sure that is this right here. That is delta y. Yeah. Well, it shouldn't just be plugging it in. You need to be thinking about this. All right. 6. There's a lot of math behind 6 that I could go into, but I'm not going to because it's just not worth it. It doesn't help you understand any better. 6 is another projectile motion problem that we'll look at some more. There's a couple ways for me to explain this. I'm going to try to do this the best that I understand it.
Which one are you on? Snowball?
6, yeah. So we're only going to look at things being launched between 0 degrees and 90 degrees because once you get past 90 degrees, it's the same thing just in the other direction. So it's not worth our time to look at 100 degrees or 120 degrees. Those would just be like negative 80, negative 70.
What number?
This is number 6. Okay, what number 6 says is that there's a snowball fight, I don't know what it is, some situation. And basically there's 2 angles that you can throw a snowball at and it's going to hit the same point. Meaning its final x value is going to be the same. Right? So there's an angle that I could throw it where it does that, and then there's an angle where I could throw it at the exact same speed and it does that. Okay. If you're looking at this visually, and this question's weird, I always have a hard time phrasing it. Between 0 and 90 degrees, there is an angle where df is the same, but the angle itself is also the same. So like, I could throw it at this angle, theta, say theta 1, it's going to reach a distance of 50 meters. Its pair angle, theta 2, is the exact same degree measurement. Does anyone know what it is? Well, yeah, you're on the right path. That's not the answer to my particular question, though. So I'm saying, like, it's not 30 and 60, it's x and x. Like, they're the exact same angle measurements. It's also the, yeah. Okay, so
45, 45.
there you go. Okay.
Jinkies.
What I'm trying to tell you, the question asks, like yours is going to be like 70 degrees. I don't know. You throw a ball at 70 degrees. There's another angle that you can throw it at to where it hits the same point. And what I'm telling you is between 0 and 90 degrees, there's an angle where the other angle is the same number. Right? And that's right here. These are what? Does anyone know the term blank angles?
Complementary.
Complementary angles, they add up to what? 90. Okay, 90 degrees. So the concept here is, if I throw a snowball at 30 degrees, I can also throw a snowball at what angle? And it's going to hit the same point. 60 degrees. Okay, complementary angles. Now this is of course without air resistance and all that fun stuff, but theoretically it'll hit the same point. Right? There's a lot of math behind that I'm not going to go into because it's just not worth our time.
Wait, so the answer is just the complementary of it?
And we'll find that out. Okay, so what angle do you think is going to give me the greatest range? In other words, the greatest x value here.
45.
Yeah, it's 45. Okay, because basically there's not another angle for me to throw my snowball at for it to hit the same distance as 45 degrees. So that's going to be my biggest range. Everything else is going to be behind it. That's another way to think about it conceptually.
So now we're doing 90 plus what
Yeah, they're complementary angles. Now there's some trig that you can do to get into that, but it's just not worth looking at. Let's see. 7. Seven's easy. If you can't get 7, then yeah. No, I'm on. 7's easy. You just use this formula. It's just straight plug and chug.
Okay, yeah.
All right. 8. For 8, there's only one thing that you need to know. Let me show you. Sometimes what we end up doing is replacing parts of equation to fit what we're given in a certain problem. So in 8, it should be pretty apparent that in 8 you're going to end up using this equation. Okay, we're going to end up using this equation, but in number 8, you don't know what A is. Okay. That's not what you're being asked to solve for. You're being asked to solve for delta D, but in order to solve for delta D, you need to know what A is. So we can rewrite this equation, and this is something that will happen a lot in physics. What could I rewrite A as? Like a simple equation, we know A equals something. There you go. And what you'll find in the problem is that you're given V and T. So we can rewrite this equation as so, and find delta D pretty easily. And that's something that happens pretty often in physics. And if you're not thinking about this and doing it all in one formula, this would be a 2-step problem. You solve for acceleration first, and then you plug in to get delta D.
Do you use the time that it gives you at the very end, or when it says what's the train displacement in the first 20 seconds of the time?
So that's a good question. You'll see in number 8, there's 2 time measurements. Okay. One is going to match the change in velocity. So one is going to say its velocity changes by this much in this much time. That's the one you use in this equation. The other one's going to say at time equals whatever, what is the car's displacement or train's displacement, whatever it is. So that time is the one you use here. Right, another thing that happens a lot in physics is we'll have 2 time measurements, and in the problem it'll be pretty explicit. It'll say, it'll tell you what that time matches up with. You just have to read it the way it is. Make sure that you're not messing that up. The rest of this.
We like to do that with throwing balls. So like, let's say I'm pitching, okay, and I pitch it out of my hand, and it takes 1.5 seconds to get to the base, right? And what I could do is say, okay, well, what is the velocity of that ball, or what is the displacement of that ball after 0.5 seconds, right? So it took a second and a half to get there. I just want to know after 0.5 seconds how far did it come. So that's something we use.
Number 9, I was getting frustrated on this one a bit. Number 9, both parts actually. Are there 2 parts to 9?
Which was good.
Yeah. Okay. Number 9, what about both parts? Okay, so number 9, what you're going to see is that you're given an initial and final velocity. What does that mean we really have? We have initial and final velocity. Delta V. Okay, so we're going to be given delta V. You're also going to be given a delta D, change in distance, and it's going to ask you to solve for T. And this really can't get any easier, actually. Which equation has those 3 things in it?
We're going to use it like 85,000 times this year.
3.
Nope. That has acceleration in it. We don't know anything about acceleration.
But we are.
Oh.
Seriously? Let's do this.
Yay! I didn't lie.
Okay. Actually, you know what? Yeah, no, that's what you need to use. Except, yeah, let's go ahead. We're gonna keep this as delta V because you're given two.
Yeah.
You're given two velocities in there. If you use it like that, you'll get the right answer. So, like I said, sometimes this is a lot easier and things will go over your head. For the second part, though, let's see. The second part you're being asked to solve for what? Acceleration. There's two ways to do the second part. Alright, so number 10, there's two ways to do the second part. One way involves using what you found in that one. The other way uses a kinematic equation. Not one of the definition ones, so not V equals delta D over delta T or A equals delta V over delta T. So just so you know, there's two ways to solve 10, but it should be pretty obvious.
Always write down your givens. And that'll
I'm not gonna, 10's
pop
not
out the
challenging.
equation.
You'll be able to figure that one out.
So 9 is just that equation.
Yep. No, I didn't.
No, it's just frustrating.
You probably did. I said I got frustrated because I thought it was a lot harder than it was.
Wouldn't 10 just be like acceleration?
Acceleration equals delta V over delta T. We don't know acceleration. That was the problem.
That's what we're looking for.
In part, you mean part, yeah, in 10 you are, yeah. Yeah, you can do that. That's what I was saying. You can use the definition equation and something that you got from the first part. Or you can use the kinematics equation. Either way, you should get the same answer.
I'm using the
Yeah,
non-square. Yeah.
You get the same thing.
Oh, okay.
What's up? Oh yeah, that was the other thing. Keep in mind, sometimes you'll have unit conversions. So if you're stuck on 10, you think you're doing it correctly, it's probably because you forgot to convert from centimeters to meters. Yeah, that sounds right. Yeah, for the time. Is that what you're talking about? 9, yeah. All right. 11 is really not that challenging. It's just a weird problem. It's a weird situation that's hard to visualize, and that's really the only thing that's hard about it. First off, though, number 11, what do we need to change about one of the givens? Yeah. Yeah, kilometers. So we're going to change that to meters, multiply by 1,000. That's the first thing you have to do. Wait, I'm thinking, no, 11's not that hard. I'm thinking of a different one. That's weird. Okay, so that's really the only hard part on 11. If you write out your givens, you're going to get delta x, a, and t. That should be pretty obvious. What direction are we moving in 11? X or y? Okay, so y values. Right. Think about the equation that we've used for the y direction so far, because it's very typical for y direction questions. That's my hint for 11. 12, once again, 12 is very similar to number 10 in that you can do 12 in two ways. You can use an answer from 10 or an answer from 11 and a relatively simple equation, definition equation, or there's a kinematic equation you can use for 12. But it shouldn't be that hard. It's very straightforward. There's not a lot of problem solving for that one. What I really want to look at is 13.
This one,
Has anyone looked at 13 yet? Sorry? Yes, 13 isn't mine. Okay, so in 13, the thing that makes 13 annoying is that you have actually a really simple situation. There's a ball that's falling. But the information that they're giving you, so here's the ball. Let's say this is where the ball started falling. Okay? The information that you're giving you has to do with a window that it's passing after it's already started falling, okay, which makes things a little weird. So what they're going to do is they're going to tell you the height of the window is, in mine is 3.4 meters. Okay, so we know, what is this going to be? So I'm going to label it as a given variable. Yep. I'm getting that from my picture. It's also going to tell us that it takes 0.4 seconds for it to fall past the window. So what is this going to be? Is it, yeah, let's do delta t. Does everyone understand the difference between delta t and t? Delta t is change in time. So what it's saying in the problem is it falls past a 3.4 meter window and it takes this long for it to do it. It's not saying at 0.4 seconds, it's at the window. Okay, it's falling past the window and it takes 0.4 seconds to fall past it. That's delta t instead of just t. That's a big distinction you need to be able to make for some of these problems. And then they're going to say something about how the velocity at the top of the window is going to be called VA, and the velocity at the bottom of the window is going to be called VB. They're just trying to trip you up. This is actually what? If I'm falling, what would this be? What would this be? BF. So we can just kind of convert it to our language to make a little bit more sense of it. All right? The very first thing it's going to ask you is, what is its, well, how does it phrase it? I want to make sure that you guys understand this. Okay, exactly. How much did the ball speed up as it passed the window? So what are we looking for? Yep. When you see a whole bunch of deltas, what type of equation do you think you're going to be using? A definition equation. Yeah. Okay. Because those are the ones that deal with changes the most, is our definition equation. So which one has all of these in it? Yeah, E equals D over T. That shouldn't be hard, the first part. It's just confusing how it's set up. But I think if you are in the mindset of labeling deltas when you know there are changes in, it's going to help you set up the problems where you need to use the definition equations. Because the definition equations never talk about a particular point in time. It's always an average over an amount of time. That's a good way to differentiate between the two. All right. Sorry? Yeah. D, it's a direction in the y. Yeah. Yeah, we're looking for delta V. Yeah. Okay, that's the first part. Number, what was that? 13, right? Okay, 14, the second part. You're now looking at what? Number 14, it's just one line. What are we trying to solve for? It tells you specifically. Okay, which one though? VA, right? So we're looking for initial velocity. Okay. So once again, we know a couple of things. What is this going to be? It's free falling on Earth. We're looking for the initial velocity. This is 14, yeah. Okay, once again, we know this doesn't change. And we know the time it takes to fall past the window is 0.4 seconds. That doesn't change. So which equation are we going to use? Okay, what else do we know? We've seen this setup a lot so far. Initial velocity, time, change in d, and acceleration. Which one? Yep. Okay, if you aren't in the mindset of knowing when to use equation 3 yet, it's going to be apparent to you. Like, you use this one all the time. And it's always these 4 variables. Well, it's 5 variables, but it's always these. Oh no, 4. These 4. I don't know why I'm saying 5. These 4 variables. Right, VIT, this is really displacement, and then A. This is the only equation that has all 4 of those in it. From there, it's just plug and chug. Solve for VI. Because we're looking, it says VA, but we know that's the initial velocity. Who did it? E and then the exponent. There's another way to do it too. Somebody did like, was it UJ? Exponents in class, you did like a space or something? E.
It says UZ,
So it'd be like
3.68 E. Yeah.
Okay. All right, 15, the very last one. This is a really good conceptual question. Yeah, you should set it up and see that's what you're being given. All right, 15. So 15, basically what it's saying is have the same windows before. I'll actually draw a window this time. Okay, but now instead of a ball falling, you have a ball that's thrown up. So now this is VA, this is VB. Okay, the ball is moving upwards. It says it's the same distance, and it takes still the same amount of time to pass the window. Now it's just moving in the upwards direction. And it's asking, will this and this part, I think they label it delta V up. So when the ball is traveling up, will the change in velocity be the same, equal to, or the same, less than, greater than, or, and then it talks about masses, something like that. Okay. So we're comparing delta V up and then delta V down from the last problem. There's really not any math you need to do here. There's just one realization that you need to make. So what we're looking at here are a couple of things. We're looking at, we have the delta T value again. And what are we looking at in the problem? Sorry? Well, no, we're not comparing that. That's the same in both problems. It's just, that's the way to set it up. What's the thing we're comparing? Okay, so we're looking at delta F. Delta V. Okay, so the question is delta V going up the same as delta V going down? There is a definition equation that relates velocity and time. What is it? There's a definition equation that relates velocity and time. Or in other words, there is a measurement we can make. This is what I'm talking about. So if we're looking at these two variables, delta V and delta T, what we're really talking about is what? Okay. What's the acceleration in the first problem? Okay. So in V down, the acceleration is 9.8. What do you think the acceleration in delta V up is going to be? Yep. We didn't change planets. The mass of the Earth didn't suddenly increase. We didn't have a chunk of the Earth fall off. So what can we say about delta V up and delta V down? They are the exact same. This is a really big part of projectile motion. Another reason why this is on the assignment is we have to realize that motion upwards and motion downwards has the same acceleration. Just because I throw a ball up doesn't mean that gravity pulls on it less hard. It's going to have the same acceleration, 9.8 meters per second squared. The other thing, the parts with the masses. Yeah, this is another big point with projectile motion. Right? If let's say I climb to the top of this roof, I make like a bubble around Stratford and I suck all the air out of it. Okay, I'm wearing like a spacesuit or something so I can breathe. So there's no air resistance anymore. I go up to the top of the school, I have a feather and I have a bowling ball. I drop them, which one hits the ground first? Same time. Right? So mass does not affect how gravity pulls on objects. So you could have eliminated those right off the bat, the ones that are talking about masses. So that doesn't matter. Another big part with projectile motion. If you're interested, one of the Apollo missions, I don't remember which one, they took a feather and a hammer up to the moon, where there's no atmosphere, obviously, dropped them. They obviously hit the ground at the same time, but it's cool to see it. Because a lot of students don't believe me when I say that. They would hit the ground at the same time. What's up? Yeah, there's atmosphere on the moon, right?
It's just small.
There's a line in it.
Okay, well.
It's small enough to be negligible.
Yeah.
Are we feeling better about this?
Kind of.
Kind
Better,
of.
but not.
Okay, the reason that this recitation was more of a homework-based one is because we need to know these equations to get projectile motion. The next time I have a recitation, it's probably going to be a little bit different. And that it won't be so homework-based, it'll be more conceptual-based. Like, if you have questions, we'll talk about them together. But it should be just as useful.
Is it gonna be like every week?
Probably.
Monday or?
I don't know.
What is the science tutorial?
I don't know if there is one.
Oh, yeah, there's a date.
Yeah, those are Tuesdays.
Can you look and see what I did wrong?
Yeah.
That's not why.
Look for this video on my website if you want to go over it again. Hopefully it doesn't take it 10 hours to complete.